So just as a quick review, we can kind of punch through it really quickly. Sig figs. How many sig figs do we have here?
3.
Why does a 0 count? Yep. Next one. 2. Why does the 0 not count? Okay. We don't have a decimal point, and it's not bound by 2 significant digits on either side. Okay. Next one. It's 3. Why do we count the 0 now? We have the decimal. Come on, Mark. We have the decimal point, and it's preceded by a significant digit. So that 0 does count. Next one. Does the 1 count? Does the 2 count? Does that 0 count? Why does it count? We have the decimal point, and in front of it is what? Significant digit. Which means that 0 is now classified as what? Significant digit. Okay, why I clarify that? Because we move to the next 0. What do we have? Okay, we have a decimal point, so what we'll do is move to the number in front of it. Is the number in front of it a significant digit? Yes, which means 4 significant digits. I know it can be a bit tricky. Upper right. We've got 2, the one underneath it. What's the deal with the formatting? Why 0 versus no 0? Okay, so the 0 in the second one is not preceded by a significant digit, so that doesn't count. Okay, so as far as our number goes, both of these are decimal point 1, 2. So they both represent the exact same thing. Why show it in 2 different formats? So we talked about this briefly, and it sounds like at least one person remembered. That makes me feel good. Okay, moving up in the world. What we're trying to do is draw attention to the fact that there is a decimal point there. The decimal point is a very easy thing to lose track of, so what we'll do is include that 0 in front of it. If you had me for lab, and you wrote the first one, you'd see a circle, arrow, and the statement leading 0. Or because for some reason I like S's, well, you'll probably see leading zeros, even though it's only 1 that's important. Okay? That's just to draw attention to the fact that there is a decimal point there. This is 0.12, not 12. Okay? So it's just a formatting thing. Next number. How many sig figs? We've got 2. We don't count either of those zeros because start left to right. Does that 0 have a significant digit in front of it? No, which means it is not significant. We move to the next 0. It has a number in front of it, but is that number significant? No. So that means that 0 can't count either. What we'd be left with is just the 1 and the 2. Questions about that? Last one? Why do we count that last 0 now? The 2 immediately in front of it allows us to count it, okay, with the decimal point. Questions about sig figs? Okay, before we actually start getting into manipulating these, there's one more thing we want to add in here, is evaluating what it means to be exact. Okay, a measurement versus an exact value. Typically when we measure distances, masses, volumes, and time, time's actually a little bit questionable in some cases. They're only as accurate as the instrument measuring them. So when we look at our measurements, we would always have this kind of error associated with it where we'd introduce these sig figs and be required to track them. But what happens if that measurement doesn't have, what was the question on this? Does not require a measurement. That's not the question I was thinking of. For instance, if I went through and counted how many people are in this room, what's the error in that?
Some people might be absent.
So some people might be absent, so that would go off my roster, but if I count the people in this room, does it matter who's absent or not? No. So what's the error in my measurement of the people in this room? Okay. Since some people in the morning didn't trust me, we can shift it to a different number. Okay? How many fingers do I have? Anybody see 3? 2.5? What's the error in that measurement? Okay, so there's a difference between a measurement and an exact number. So when we look at the error in counting 4 fingers, okay, I'm not counting the thumb because that's not a finger, it's a thumb, right? Okay. Looking at 4 fingers, it is exactly 4 fingers. It's not 4 fingers plus or minus a fraction of 1. There are exactly 4 fingers. What does that do as far as sig figs then? All right, and this is going to become important when we start to add and subtract different things. How many significant digits does that measurement now have? Digits, huh? Get it? Like fingers?
I think significant digits don't qualify for exact numbers, it's just measurements.
Kind of the right idea, but we can't say it just doesn't qualify. So what we're going to do is actually push it to the absolute extreme. What we're going to say is an exact measurement has an infinite amount of significant digits, which means if we go through and try and run any calculations, there's so many significant digits in it that it's not going to impact our calculations. Okay? So we'll only evaluate the measurements where we have error associated with it. So in this example, we could look at an amount, okay, or a number of things. How many quarters are in that picture? 7 quarters. Not 7.3 or 7.2. There are 7 quarters. We are counting a physical number of these things. There is 0 error in that measurement or that observation. And we can show that by saying that we get an infinite amount of significant digits. Does that kind of make sense? The exact measurements don't show up a lot, but they do show up every so often. So when you see an exact measurement, you can be thankful because that's not going to impact how you do any calculations. Your later calculations are going to come solely based on your other measurements or your other numbers. Okay, so what do I mean about that? Why do we care about significant digits? Because at this point, in theory, all we've done is just looked at what some magic numbers are and said, okay, this is how many numbers are in it. In the real world, we'd have an instrument. The instrument would spit out these numbers, and we would keep all of those numbers because the instrument is telling us it's accurate that far. If we got rid of that information, what we're ultimately saying is we didn't trust the instrument. Well, we don't trust the instrument. Why did you use it in the first place? Okay, so any number that comes out of an instrument, regardless of where the decimal point is, you want to record and report in your observations and measurements. Because otherwise, you're making it null and void or nonsensical to even use that instrument to begin with. Okay? So, where does that come into play? Is now when we take those individual measurements and we try and do different mathematical operations with them. How does that affect our end result? Which is a complete opposite of what you may have seen with mathematics. When we add 2 numbers in mathematics, we get an answer. And that answer is it. We don't have to worry about rounding anything. That's our answer. When we get to science, in general, actually all science fields, we have to be very careful about what we report. It has to have the correct accuracy based on the measurements that we took. Okay? So there's 4 main operations we can do, and we can classify those in 2 categories. So we get addition and subtraction, which we'll evaluate first. Okay? If we're going to translate our error through our calculations, when we're looking at addition and subtraction, the result, or our final answer, is only as accurate as the least accurate measurement. Okay, so which of these 3 measurements is the least accurate? This is where we've got to be careful.
114.3.
Okay. I heard a lot of people say 114.3. Everybody agree with that? So I count sig figs, the second one has less sig figs. What do you think is more important? It's going to come out to the decimal places. Okay? So in our very first measurement, we can only measure as accurately as, you have to help me with that, that's the tenths place, right? Whereas all the other measurements go out further decimal places. Okay? So our first measurement is actually the least accurate of those, regardless of the number of sig figs. So that's something that's interesting in the addition and subtraction. We don't have to worry about how many sig figs there are. We just need to know which one's the least accurate. So we'll look at our decimal values. So when we go through and add this, make it just as embarrassing as this morning because I don't remember any of it. We could add this up and we get what? 2, 6, 3, 13, right? And 16. Carry our 1, we get 115.63362. That's what our calculator spits out. We got a lot of numbers in there. Only some of those numbers are we allowed to keep. Which of those numbers will be reported in our final answer? 115.6. Our answer is only as accurate as the least accurate measurement. So when we go through to report our final answer, we would show it as the 115.6. The rest of those numbers, we don't have enough information about to reliably prove that that is a 3362. Without that extra information, we don't know what those numbers are. We have to stick with our least accurate measurement. Yes?
So our answer can only go as far as the smallest decimal.
As the smallest decimal value. Exactly right. This is only addition and subtraction.
And this is called significant digits?
This comes back to significant digits. It's how do you apply significant digits in different mathematical operations.
Okay.
So what we've looked at so far is just counting the sig figs, or the significant digits, significant figures, however you want to say it. Now what happens when we do a calculation afterwards? So why is this important? Well, we go to the 2 examples that we've put up here now. For that first number, what I went through and did, it was propagated it all the way out. Okay? Our instrument didn't tell us what that number was, so let's pick it as the smallest number. Let's just throw in a bunch of zeros. Okay? Our instrument also didn't tell us that it couldn't have been 9, so let's make them all 9s. And now if we go through and do our mathematics or add these 2 up, do we get substantially different answers? Yeah, it makes a huge difference in our overall answer as far as the accuracy of those numbers go, which means we want to make sure that we don't include that information because it could very easily have been in the case where we're all 9s afterwards, or it could have been in the case where they were all 0s. Since we do not know that information, we will not imply it in our final answer. Does that kind of make sense? It only gets more complicated. Okay. Ooh. So what happens if we shift to another operation? Let's look at multiplication. Yes?
Okay, sorry, just
Nope.
going back to that, the last slide. So for example, the second one at the top with all the zeros.
Yep.
You could still only go to the next over decimal place because those aren't all significant figures.
So here's where we've got to be careful. And our new cases, the new examples that I drew up here. Okay, what's our least accurate position? Our least accurate position is all the way to the end. How do we know that? What's that?
Because they've all got them. Why do they say that?
I don't quite accept they've all got them,
Well,
but I
the
think
top
I heard it
one is
right after.
Significant figure.
How many sig figs are in that first number?
3.
1, 2, 3, 4 are all significant. There's a decimal point, which means any 0 that is preceded by a number is significant. So that 0 is significant. What about the next one? And the next one? And the next one. As soon as we put in those zeros, now they're significant. Whereas in this first place, we didn't include them. Why did we not include those zeros? We didn't know what they were. Okay, we didn't know if it was a 0 or a 1 or anything else.
So our answers would then need to include
All of those numbers. Exactly right. So the intent with these 2 examples on our far right is to say, how does that impact? If we went through and said that those were indeed zeros and actually translated the answer out,
then it would have all those preceding numbers.
we would need all of that extra information. And how much of a difference does that make in the final answer? So the idea is that you compare the answers between these. Should I add these up to compare them?
No.
Okay, I really wanted to know. Should I add them up? Okay, let's go ahead and add them up. Way to embarrass me again. Let's give it a shot. So our first one, that was 115 point what? Someone wrote it down. 63362. Okay, there we go. Deep breath. We can add, right? 7, 3, 3. Hate doing that. 115. Oh, and this one was really bad from this morning. I remember this. So 0, carry our 2. So it's 26. That's a 2. 13. Did you just say 14? You're right. This is why we invented calculators. We just have to know how to use the calculators appropriately. 10, 23. Okay. If we now compare across, you'll notice that we can get a substantial difference in the numbers. Here we're looking at 0.7 versus 0.6. Okay. So if we assume that those are 9s, that makes a big difference than if we assumed that they were 0s. Okay. So when we come up with our number, we can't make that assumption because our instrument didn't give us that information. It only measured to the 10th place. As soon as we bring in some other numbers into that position, we're now adding numbers. We're making stuff up and hoping it works. Problem with making stuff up and hoping it works is unless it's a multiple choice exam, probably not going to work. Make sense? We're a little bit more confident with the addition subtraction? Okay. So, multiplication and division. Now our rule changes slightly. So in this case, our result is only as accurate as the measurement with the fewest significant digits. So to me, these are nicer because I don't have to worry about which is the least important or the least accurate. I can just go back and just count significant digits. So we would go through and count the significant digits in each of our numbers. 7.28, we have how many? 4.6. We have 2 sig figs. So we would go through and set up our multiplication. How do we figure out the area of a square? Length times height, or width times length, however you want to say it. And we can multiply those two together. And if we take a look at our calculator, we'd get 33.488 units, technically squared. Of those, how many are actually a value that we are allowed to report? We go back to our sig fig rule. We had 3 and 7.28. Whoops. It's not a 2. And 2 and 4.6. According to our rule, we can only report as the fewest significant digits, which means our answer needs to be reported to 2 sig figs. What's our answer need to be? 33. Why am I hearing 33 and 34?
Are we not rounding then, or?
Okay, we haven't talked about rounding quite yet. I tried to pick an example where rounding wasn't going to show up. If we're going to round, we would shift to that first number. Okay, if it's less than 5, which way does it round? Down. We don't worry about the rest. We'll only look at that first insignificant number. Okay, we will look at that in a second. So when we do multiplication, it comes back to our fewest sig figs, and our answer gets reported as 33 units squared. Okay? What if we did division? Same rules apply. Okay? And why again? So if we went through and changed that number after the 6, we said maybe it was a 9, what happens? Our answer substantially changes. Okay? We don't see that same result. And that's because we don't know that number. That could be anywhere as close as 0, which we assumed at first all the way up to 9. If we make it 9, do we see a substantial difference in our answer? One case we said 33, in the other case we said we get 34. Okay? That makes a substantial difference in our overall answer for whatever we're trying to do. We need to make sure that that error doesn't show up in our calculation. And we do that by always rounding according to the least significant digits, so 1 and then 2.
So the bottom one, they both have the 3 significant figures, or it'd be 34.1?
So if we were going to propagate that all the way out, officially, yeah, we would report that as 34.1. Good question.
Why again, on the first one, don't we do 33.5? Why would we run that before?
How many significant digits are you allowed in your answer for the first one?
2.
So according to our multiplication division, we look at our sig figs. 3 for the first one, 2 significant digits for the second. So we go to write out our number. Our first answer is 3. There's 1 significant digit. What's the next one? 3. We are now out of sig figs. I'm not allowed to write any more numbers. Okay. So the 33.5, you think, oh, that's more information. But is it 33.5? That assumes the number was a 0. If it was an actual 9, it's actually 34.1. Okay. So we don't want to imply information or add information that wasn't given to us. The instrument must give you all of those digits. If it doesn't specify, you have no idea what that number is. You have to go based off of the least number. Does that make sense? Okay. I know, it's very counterintuitive to everything you would have ever done in the real world. But that's how it has to work in these cases. And that's because in very particular circumstances, these distance or the changes in these numbers is substantial enough that it can cause a space shuttle to explode. Okay? If you look at, is it Discovery or Challenger? I forget which one. There was an issue with one of the O-rings. Okay? Some of that was just how someone was measuring the properties of the O-ring. If they measured with the appropriate number of sig figs, maybe that would have translated across into something else. Okay. Yeah, and it's actually not a sig fig issue, but I was hoping nobody knew, then it didn't matter. I could make it up. Okay. So sig figs do make an impact in the end result. We want to keep as careful control over all of them, and in that way when we tell somebody else to rerun our experiment, they can directly compare. Because if somebody else can't match our results, your results are useless. Okay? You cannot use those for anything. Okay? So that's why these rules were kind of created and used consistently. Other questions with our multiplication and division? Okay, we did come up with the issue with rounding. So if I went through and changed the numbers a little bit, and we now go through and process for our addition and subtraction. How many sig figs? Or sorry, to what place do we need to go? Which one's our least accurate measurement? Since I fired off 6 questions, you can answer all 6 at once, right? Which is our least accurate measurement, the first one or the second one? First one. Which would mean we need to measure our answer, or report our answer to the, is that tenths, hundredths place? So when we go through and look at our answer, when we do the addition, we get that number. Our answer comes out as 1.33, but now we've got an issue. Okay, a 5. That's starting to get it pretty close to being 1.34. Or is it 1.33? Which way do we go? We're going to need a rule to come up with that. Okay, well, what happens when we multiply? Maybe we run into something similar on the other side. Let's take 7.8 units times 4.68. How many sig figs are allowed to show up in our answer? How many sig figs?
2.
It's 2. It's the 7.8 is going to trump here. We get 2 sig figs, so we go with 36. Well, now that's 0.5 again. Does that 5 mean it's closer to 37, or is it closer to 36? Ow. So I intentionally picked something floating right in the middle. So what we want to do is come up with some standard rule, and this is where we get our rounding rules. If the first non-significant digit, so in the case of our addition and subtraction, we said we had 1.33 those were all significant. So our non-significant digit is that 5. If that first number is less than 5, then we just report our significant digits as is. So our answer would be 1.33, which is what we did in the previous case. We didn't have to worry about a rounding issue there. If we move to rule number 2, though, or we can now shift to rule number 2. That box didn't show up, so let me try that again. If the first non-significant digit is actually greater than or equal to 5, that was supposed to show up, then we will add 1 to the last significant digit. So in the case of our addition, the answer that we report becomes 1.34. Okay? And because I made a big deal about it before, what's wrong with that number? Doesn't have the units carrying after it. 1.34 grams. What happens with our multiplication and division? Said we can carry to 2 sig figs. So our answer is 3/6, but now we have our first insignificant digit, that 5. If it's equal to 5 or greater than, what do? We add 1 to the previous digit, and our answer becomes 37, what do I have, units squared? Okay. Why do we do that? Why not round down if it was equal to 5? Good question. I don't know. Okay. Where do these rules come from? Somebody decided to put it down on paper and try and be consistent with it. Okay. Even when we come back to measuring distances, we created a meter to represent the exact same thing around the world. Okay. That meter was something that we arbitrarily decided. Same thing's kind of going with our sig figs and our rounding. We want to make sure that when everybody goes through and runs these calculations, everybody gets the exact same answer. If you get a different answer, even if it's a small difference, 37 versus 36, that can translate into a huge error in the real world, and we want to avoid those as much as possible. So the idea is that we try to follow these rules as accurately and carefully and make sure that everybody else follows them the same. Okay? That said, I'm not a fan of rounding, and it usually bites students all over the place, okay? And not in a nice way. So where else does it become a problem? If we move to rule number 3, what if you have lots of individual calculations to go through and do? If you have a huge sequence of calculations, each with differing significant digits, you're then going to have to worry about when should you lop off the insignificant digits. So to get around that, what you're going to do is round at the end of your calculation. Keep all of the significant digits all the way through your calculation until you get the very end. Then you can work your way back through and say, okay, I need to get rid of this, shift here, all of that fun stuff. Okay? As long as you do that, you should be okay. Most of your calculators will store that information so you can see it, and it will continue propagating all of the sig figs, even the ones it doesn't show you, all the way through your calculation. If you're somebody that likes to individually stepwise out each individual calculation instead of running them into a string, that's okay too. Just remember, if you're going to do a single calculation first, you have to make sure that you report enough sig figs that when you go through to condense and round at the end, it doesn't impact your overall answer. So if you're supposed to have 3 sig figs, when you look at your first answer you should have probably 6 or 7 sig figs written after it. And you're going to get rid of most of those. But if you get rid of them too early, that'll change your end result, sometimes substantially enough that you won't be able to figure it out based on the multiple choice test. All right? So make sure when you go through to attempt these rounding rules, you're at the very end of your calculation. Questions? Really? Nothing? Crystal clear? Close enough? Next thing that we'll do is look at some simplifications, kind of adjust how we approach things. So this is a nice little fun exercise. I'm going to have you write down in your notes 4 times 4 times 4 times 4 times 4 times 4. All right. Now that you've gotten that written down in your notes, now you can go back and enter that into your calculator. Because remember, all of the problems that you're going to end up working, at least as far as the homework goes right now, you have to write out the question and then your answer. So you can go through and write this all out. Okay. As you're writing it out, kind of delaying getting most of you to actually do this, you're going to find that your arm's going to get pretty tedious or tired, particularly if you have 20 of these problems to work. Okay, so we would hope that someone invented some kind of simplification. What's that simplification? What's that? We'll look at powers, okay, or exponents. So what we can go through and do is now simplify this and say, instead of writing it out all like that, just write out 4 to the power of 6. So a 6 is a superscript. And if we go through and now attempt to put this into the calculator, you'll notice you get the exact same answer with a whole lot less work. So what we just have developed or created here was an exponential factor, which allows us to process the mathematics a lot faster without having to write stuff down or punch as much stuff into the calculator. Right? The less stuff you can write down, the less stuff you put into the calculator, the better off you'll be. All right? I will bring a note about calculators here. You should make sure that you can go through and do this and you get the same answer. Do the 4 times 4 times 4 all the way out, get an answer. You know that is now correct. Okay, you might even test it a couple times, make sure you get the same result. Then go through and look for these other features. You might find something noted as the EXP, which I'm pretty sure in most cases is referring to a power of 10. Okay. You might also see an x to the y position. So you could go through and enter 4, then push that button, and then push 6. And what that's mathematically doing is going to give you 4 to the power of 6. Last one, this is probably the one I'm more comfortable with. You can just use the caret symbol. The caret symbol is raising that number to the 6th or putting that next number as your exponent. Okay? Make sure you are comfortable with doing this on your calculator because that can make your calculations a whole lot easier. Questions about that? Okay, so what we just looked at was exponents. We're doing is saving your risks by simplifying what you have to write down, okay, condensing it. There are a couple common terms that you'll see that are also associated with exponents. You'll hear the terms squared and cubed more commonly. What's happening with squared?
2 times.
Let's say it is the area to the, a squared, okay, a to the 2nd power. Why do we say squared? What was that? You're not doubling it. You got to be careful with that. We take a look at a square. What's the length of a square? Pick a number. 2. What's the height of a square? 2. All the sides are the same. So if I want to know the area of the square, what do? I multiply those two numbers by each other, which is the same as holding them to the 2nd power. What did I just find the area for? Square. There's our squared terminology. What about cubed? That's holding it to the power of 3. Why do we call it cubed? How do you figure out, was it the volume of a cube? Length times width times height. If it's a proper cube, what are all those numbers? The exact same. So now we have a cube. That's where those phrases are coming from. The other place where you'll see it less commonly is you might see anything held to the something power. So in this case, I decided to be cheeky. I guess I was tired and wrote Mike to the x power. So if we were going to write that out, mathematically, we've got Mike. Just to make sure that we know that it's the entire Mike, not just the e, raised to the x power. Okay? So that English allows us to translate into the mathematics, right, which is something that we'll find throughout the semester you're going to have to get comfortable with. The English means one thing, you're comfortable with it, oh, I know how to translate feet into inches. Now do it with the mathematics. So you have to be able to convert both. Questions about any of that notational stuff yet? Okay, the next big thing that we'll see is powers of 10. These are really used just to simplify those, insignificant zeros, or as the textbook's been calling them, the placeholder zeros. So what we're going to do is convert a number that may have been really big or really small, and we'll convert it into scientific notation by using these powers of 10. We'll look at scientific notation in just a second. Okay, so our powers of 10, pretty much just saying we're going to multiply whatever our number is times 10 to some other number to account for all of our zeros. So they went through and listed a whole bunch in your textbook as far as what each of those numbers mean and how it shifts your decimal point. So really our powers of 10 just allow us to define where our decimal point is located in hopefully a simplified number. All right? So this is where we really use that as our scientific notation. Again, as you'll find that I at least like to do a lot, most chemists tend to be lazy whether or not they admit it. Okay, so they will come up with whatever notations they can to simplify their lives, as we've already seen. Okay, if you're going to refer to the element carbon, what are you going to tell me? It's C. Why do we call it C and not carbon? We're lazy, and the arbon is way too much effort to say. We say, oh, it's C. Okay? Same deal with all the other elements. We come up with these simplifications. We're just too tired to say the full name. Okay? Or write it out. So scientific notation. We're taking a really big number. I did make a typo here that's fixed on the next slide. Let's make this a 0 and a 0. So we take a very large number, and what we're going to do is attempt to convert that into a different format that allows us to see it a little bit easier, right, without having to draw in all of those zeros, because we're way too tired to do that. Same kind of idea with really small numbers. What we're going to try and do is convert that really small number in such a fashion that we can get rid of all of those zeros. Because when we look at our really small number, how many of those digits are actually important? How many of them are significant? I heard it faintly there. We only have 3 significant digits. The rest of the zeros we care less about. All they're really doing is telling us where the 1, 1, and the 6 are located. If we go back up to our first number, how many digits do we really care about in that first number, assuming those are zeros? Okay, we only care about those first 4. The rest of the zeros are there just to kind of allow us a frame of reference to figure out where the rest of the numbers are located. So that's what we're going to try and use to figure out our scientific notation. So what we're going to do is convert our overall numbers to a different format where we will list off our significant digits. Write that out a little bit. Followed by this multiplier factor, which represents all of our placeholder digits. Whoops, not digits. We only have one number that we can use as a placeholder. What's that? Our placeholder zeros. All right, so that's kind of our intent behind how we build and simplify these things. Okay, so what do I mean? Here's the part where we've got this set up. So step 1, what we're going to do is place our decimal point after the first significant digit. And then we'll add on the rest of our numbers as necessary. So if we look at our first example, what's our first significant digit? 4, followed by our decimal point. And then we have 0, 6, and 3. Okay. We won't include the rest of the other zeros because this is where it could be actually kind of tricky, which might be the rumbling I was hearing. Why do I not include the rest of the zeros in this number? They were not significant in our first problem. Why were they not significant in our first problem?
Because there's no decimal.
No decimal point. As soon as we shift into our new notation, we We have a decimal point. So if I include those zeros, what am I saying? They're significant. So we have to be careful when we do this translation that we don't turn zeros that were insignificant into significant digits. So you have to stay super consistent with it. And this goes beyond just consistency. This has to do with the accuracy of the measurement. In our first case, what I'll underline now in red, our initial distance, our non-scientific notation, those zeros we didn't know about. They're just there to hold the location to force the other numbers to a higher decimal value. Those could be ones, twos, tens. They could be zeros for all we know. We don't have information about that. If we shift to our scientific notation and now include those zeros, they've now become significant. It's not that they are any number between 0 and 9. They are now exactly 0. So we'd be adding information that we didn't have. We'd actually be changing the number. Does that make sense? All right, so now the next part. Indicate how many places you moved. Sorry, there wasn't a pause there. Moved the decimal in place of the n. Okay, so our n is where our scientific notation comes in. So what we're going to do is now multiply by 10 to our n. So our n is how far we shifted the decimal. We go back. There is an implied decimal point here. It's not shown, but we can now re-imply it. We shifted our decimal point 1, 2, 3, 4, 5, 6, 7, 8 positions to the left. So what we'll do is it is now 10 to the 8th. Is that positive or negative 8? How do you know it's positive? Okay, there's a variety of ways we can come up with it. The way I'm going to stick with, so we can avoid some of that, is if we shifted it to the left, it's positive. If we shifted it to the right, it's negative. Okay, so we'll just go based off of the physicality of what's happening and try and memorize that information. Okay? So that would be positive 8. What's fun about positive numbers? True. How often do you specify that a number is positive? You don't. Okay? We don't need to include the positive value there. We can just say it's 10 to the 8th. All right? What happens with our next number? What number do we start with? 1, followed by our decimal point, and then 1, 6. We don't have any other significant digits. We can then multiply, sorry. Oh, thank you. Tag our unit out there at the end. Okay, good call. And good call for not rubbing it in very well either. Followed by 1.16 times 10 to the, now we've got to figure out how far we shifted the decimal place. 1, 2, 3, 4, 5, 6, 7. Which way did we shift it? To the right, which means negative. Okay, this time I kept my unit. Okay, this way we can generate our scientific notation and work from there. Okay, so this is our base scientific notation. We can adjust and make it a number larger than between 1 and 9. We can jump up to 10 to something, but that's just going to shift how far we're adjusting our decimal values. Okay? One other fun thing to notice, you notice the kind of little cloud shapes underneath all the zeros? If you ever borrow someone's calculator, take a look at the screen. Usually about 90% of the time you'll see these little cloud shapes drawn onto the screens. Okay? So feel free to do that too. It adds character to the calculator. Okay? Allows you to help process some of these. Questions about scientific notation? Okay. We will manipulate these here in just a second. By a second, I mean longer than a second. We good with scientific notation? Okay. So that is the end of our PSS chapter. If you're using edition 7. If you're using edition 6, that was the end of chapter 2. So edition 7, we're now moving into chapter 2, which is the metric system. We've already discussed some of this when we looked at kind of qualitative observations. Now we're going to start to look at it more quantitatively. You'll notice also there's a giant space of white where you would expect to see some homework questions. I completely forgot to look at the textbook to try and find some problems. So I will take a look at that tonight and hopefully get you a list of questions that you can work from this chapter. All right, so I apologize for that. Metric system. So, fun thing, I always have to kind of accept my failures here. You know the fun history lessons that we were talking about on where the different units came from and how it was neat, and it was the king's foot, king's thumb, all that. Turns out I was wrong, but partially wrong. I mean, the king did make a big deal out of it, but it really came back to the Greeks that apparently were the first ones to introduce the whole inches and twelfths and foots and stuff like that. And then we can blame the French for the scientific unit, or scientific units, not really, the SI units, okay? Your textbook does a nice little discussion of it. I think my history was more interesting, but I guess theirs is more true. Okay? We go through and look at what happens with our metric system. We've got our standard units, which we already discussed. So when we measure lengths, we're looking at meters as our base unit, mass is in grams, volume, liters, and time in seconds. If we want to scale away from these, we want to go to bigger numbers or smaller numbers, what we want to do is have an easy way to shift to those larger systems. Much like when we look at inches versus feet. Okay? Feet is multiple inches, but we'd have to remember the term inches and feet. Okay? And if we want to go to even larger distance, yard, well, what's the connection between a yard, a foot, and an inch? That's yet another relationship we'd have to have memorized. So the hope between the SI system is that we can now go through and use simple prefixes to scale upwards. And we'll use those prefixes in very particular fashions to mean the exact same thing. So if I assign a prefix to meters and then use that same prefix to one of the other units, it means the same multiplying factor. Okay? So what are some of those prefixes that you've heard of? Anybody? Kilo, big one. Milli, centi, micro. Okay? All of those are implying ultimately a power of 10. So that's why we talked about the powers of 10. We can now scale larger or smaller based on what that prefix means. So we have to know what the prefix is and what it mathematically means. So what we're looking at is these Greek prefixes. This is pulled straight from your textbook. And they imply a power of 10. So if we convert our numbers into scientific notation and look at the power of 10 followed after it, we could then get rid of that power of a 10 and bring in a prefix in front of our unit instead of showing the powers of 10. Okay? So you've got periodic table. You now have all of these memorized. That's a lot of fun stuff to get through, right? Is there anything else? Did I miss something else? What else did you need to memorize? Is that it? Oh, well, that's easy. Shouldn't be a problem for you. If you attempted to test me on these, I think I know 5 or 6 of them. Okay? So it's not required that you memorize them all because you don't see them all very often. Okay? What ones do you expect to be using super frequently? Kilo, centi, and milli. Okay? Can't guarantee it, but I'll kind of throw it out there as an empty threat. If you do not have those prefixes memorized by the end of the semester, you will not pass the class. Okay? There's probably other reasons why you wouldn't pass the class if you didn't memorize these. Okay? So these absolutely you need to know because you will use these 3 quite frequently. The rest of them do show up, particularly in questions in your textbook, but they show up much less frequently. Questions about that? Okay, so should we come up with some ways to apply? Since it looks like you're still writing, let's take a look at something else. The nano unit. Okay, why would we pick out the nano unit? Okay, it's tiny, but it has even more importance. How many people have heard of nano before? Okay, a few people have heard of nano. Why have you heard of nano and say not pico? How many people have heard of pico? Okay, a few people have heard of pico. Why is nano more popular than pico? Because for the last 15 years, if a scientist wanted money, what did they do? Put nano in front of whatever they were working with. And now everybody goes, oh my gosh, here's some money. Okay, it's just kind of the way funding works. You find a keyword that everybody freaks out at, and you say, I'm doing that. Okay? Everything that a scientist does works on the nano scale. okay, unless you're an engineer, and even then, we could probably push some nanoscales. So if you hear somebody going, oh yeah, I'm working with nanoparticles, everything you were working with is nanoparticles. Okay, wake up, it's not that bad, okay? The other fun part about it, now that I go through and make fun of the nano people, I worked with a nanosecond laser. So what it did was pulse laser light every nanosecond. And we would then use that time scale to monitor different things. Okay? So you've ever seen a strobe light, people moving through strobe lights and get an idea of what's happening? That's what I was doing with molecules. We pulse a light, we see, oh, it moved. Okay, now what happened? Light's out. Oh, light came back on, they moved again. Okay, how did it jump between those? So we can use these things for different properties. So let's kind of go through a brief interpretation of this. So what we're going to go through and do is convert our numbers over to scientific notation and then evaluate our number with its new unit. Okay, so we're going to do effectively a unit conversion without getting too converty on it. So let's convert our first number into scientific notation. What do we get? Should have 1.2. And now why the times? Why don't we have some zeros in there? Why do we not show these zeros? It's not just scientific notation. Those zeros weren't significant digits. Okay? That's why those zeros don't show up. How do we know they weren't significant? Because we remembered all those rules that we went through and processed stepwise through. So 1.02, our implied decimal point, we've got here, we shifted 1, 2, 3 positions. So we have third, is it positive or negative? Positive. Shifted it to the left, so we're looking at a positive value. Another way we could look at it is the number big or small? Number bigger than 1. Is 1200 bigger than 1? Yes. Yes. So that means our exponent needs to be positive. Okay? What do I mean by shifting to our number and our new unit? Well, did I put in? Oh, I did put in units. There's our meter. So our number is 1.2. What's our new unit? Well, our new unit is going to incorporate that 10 to the third and meters to give us our prefix. And what we get for our prefix is the K for kilo followed by meters. So what we've done is now converted 1,200 meters over into kilometers. Our powers of 10 imply those shifts. Whoop. What happens with the next one? What's our number? It's really original. 1.2. What do you think the next one is? Okay. What's our multiplier for our seconds? We go 1, 2. So we shifted to 2 places. Whoops. Give me some space in there. Is our number bigger or smaller than 1? Smaller, which means has to be a negative 2. We include our units of seconds. When we translate across, what do we have? 1.2. Our prefix is centi, followed by our seconds. Kind of makes sense? Okay, what happens with the next one? Yeah, I wasn't very creative on that one. I saw it. I'm sorry. We get our centi. Yep. It doesn't have to sound right. That's what it is. All right. And the last one? Shift our decimal point. 1, 2, 3. Bigger or smaller than 1? Smaller, so it's got to be negative. Grams. Whoa. Let's try that again. When we go through, we can look at our unit break, and we get 1.2. and our milli prefix in front. Okay? Make sense? So at this point, what we're doing is shifting the units over in whatever fashion matches the prefix that we wanted. Okay? It's not always going to be that way. You may be asked for, in say that first case, asked for decimeters, not kilometers. So you'd have to come up with a new method to set up this conversion, or you can come back and relate all those different calculations. So what we want to do is now try and come up with a more generic form for trying to solve these things. Okay? So by doing that, what we're going to do is take a look at our prefixes. We're going to try and mathematically manipulate these into something useful. Okay? So when we take a look at the English, there are 1,000 meters in 1 kilometer. Mathematically, it means the next statement. 1 kilometer equals 1 km equals 1,000 meters. We can manipulate that equation around a little bit. Okay, what do I mean? Well, let's take a stab at it here. If we take 1 kilometer, say that equals 1,000 meters. Now, why do this? Well, let's take a step further away. Let's go back and say, let's do 3 over 3. What's 3 over 3 equal? 1, right? Okay. You guys got that one awfully fast. Let's try this again. How about A over A? Still 1. If A, let's pick a number for A. What does A equal? Okay, I heard 2 and 4. Let's stick with 2. Okay, 2 is magical. 2 divided by 2 equals 1. So it doesn't matter what we do. As long as we're putting the same thing over the same thing, we're still multiplying or getting 1 as our answer. So what we can go through and do is say, okay, I'm going to multiply both sides of this equation. No, let's not do it that way. I forget the mathematics on this. We go through and multiply, let's say, one side by 1 kilometer over 1 kilometer. So the equation now invalid. It's still true. It's still true, right? Okay. So what we're going to go through and do is, instead of multiplying by 1 on one side, what we're going to do is kind of split that 1 up across the equation. So what I'm going to do is now divide both sides by 1 kilometer. And so that's slightly different. But if I now multiply the right by kilometers, I have to do the same to the other side, and kilometers cancel, and we still get 1. So mathematically, nothing crazy has happened here. Okay, but what's 1 kilometer over 1 kilometer? 1. Okay. What I've done is now converted that English statement into something that we can now mathematically use. We've got a numerator and a denominator. Okay, everybody's favorite relationships. We're going to build on this numerator-denominator relationship to be able to convert different numbers or different units into different systems. Okay? So what do I mean by that? Well, that's our conversion. Okay, what if we done, instead of that division, let's say we did it the other direction. Let's say I divided both sides by meters. Is that still equal to 1? I know it's kind of crammed in there. Yeah, it's still effectively the same thing. So what can we do with that? Let's go back to the problems that we were working on the other side. We started with, say, 1,200 meters. And I want to convert that into, say, kilometers. Well, in this case, what I'm going to go through and do is multiply by 1. Multiplying by 1 is a valid thing. I take 1,200 meters and I multiply by 1. What's my answer? 1,200 meters. Okay, well, that's kind of boring. Let's tweak it a little bit. I'm going to multiply it by 1, where it's 1 kilometer. That's 1,000 meters. Well, what does that do for me? What happens to this meter unit now? They cancel out, just like they canceled out, or just like our numbers canceled out earlier. So what we can do is now cancel those units. All right, well, what does that do for us mathematically? Well, we could now rewrite this as 1,200 over 1,000 kilometers. All right, how many of you like fractions? Okay, so let's simplify that. Punch it into your calculator. What do you get? What was our answer from our last problem? 1.2 kilometers. So what we did is now, instead of converting through scientific notation, converted through what the textbook is calling a unit factor. Okay. Everything we're going to be doing for the rest of the semester is dealing with these unit factors. Depending on what that unit factor is, we might give it a different name. In some cases, we call it density. What is density? It's a conversion between one unit to another. What did we just use this unit factor for? That 1,000 meters over kilometers. What was the whole reason we used that? We used it to convert meters into kilometers. It's a conversion. Okay. Why can we do that? Because just as we just proved, it's mathematically equal to 1. All we're doing is multiplying by 1 and letting our units kind of trail for us to do that, help with that conversion. Okay. Kind of makes sense? Okay. Let's pick a trickier one. Oh, well, we can list that up. So there's our numerator and denominator with our unit, sorry, not our unit conversions. What do we call them? Unit factors. You can see I really like calling them unit factors. Okay, those are our unit factors that can allow us to switch our units around or convert them from different things. Okay, so let's pick a more difficult one. We could take our centimeters. Okay, why is this one more difficult? Okay, when you look at your bank account, please let me know when you panic. When you see a positive number or a negative number? Negative number tends to make you panic. Why? Because it's the opposite of your positive money. Okay? Same thing's happening here. As soon as most people, and this isn't just you, I panic just as much as you do, as soon as you see that negative symbol and the exponent, our heart skips a beat and go, oh crap, I'm going to panic now, something's wrong. Okay? So what we're going to do is evaluate that negative symbol in a couple different ways. Okay? First way is we're going to try and keep it as simple as we can here and go through the same logic that we went through already. We can generate our unit conversion or unit factor by taking our equation 1 centimeter, 10 to the negative 2 meters. We can divide both sides by our 10 to the negative 2 meters. And what we get is our new unit factor. Equals 1, right? So we're now able to convert centimeters into meters, or meters into centimeters, rather. So what can we do? We could go back with the numbers that we had before. I don't remember what they were, so let's pick one that's going to be a little bit different. Nice little happy tree there. Okay, somebody laughed. Good. Okay. We've got that 0.0012 meters, and I want to figure out how to convert this into centimeters. And we went back to the problem that we looked at. The initial way that we discussed it is we could only convert this into what? Millimeters, right? Yeah. Okay, so that's not very helpful. I want centimeters. So what we'll do is multiply it by 1. But our 1's going to be a special one. It's going to be 1 centimeter divided by 10 to the negative 2 meters. If we follow our units, our meters can now cancel, as we've seen before. And we end up with 0.0012 over 10 to the negative 2 centimeters. So, any ideas why this might make people panic even more?
They're not in the same form.
Okay. We now have all sorts of numbers floating all over the place. And we have a negative 2 in here. Makes this a big mess. Okay, what we're going to do in a second is look at a mathematical simplification of this. Okay, it definitely tends to lose people a little bit, so you can either like it or not. It's up to you. If you don't like it, how would you solve this problem? A little black box with some buttons on it, a little screen. Punch it into that little thing and spit out some magic numbers, and those magic numbers be your answer. Okay, you don't have to worry about doing anything else. You can solve that directly and get your final answer for the units in centimeters. Anybody know?
Well, 10 to the negative, if 10 to the negative 2 is 1 centimeter, isn't it just over 1?
Anybody got the calculator in front of you? You can punch it in. 0.12 centimeters. So this brings up two fun points that I want to address here. Number one, it looks deceptively easy to do in your head. Okay? Fun thing about doing things in your head, this is a life lesson when it comes to exams, so it's kind of a big deal as far as I'm concerned. We're done at 55, right?
Yeah.
Good. Okay, so we'll get exactly where I want to. How many of you, when you walk out of the test, feel all happy and light? Every single test you take. Okay. 2 out of 48. Those are some good odds. How many of you, when you walk out of a test, your head is kind of shaking, hands are a little bit nervous, going, oh my God, life's going to end? Substantial amount of you. You got that kind of buzzing headache, right? Okay. Your head's hurting because you were thinking. It's a good thing for a test. How much thinking should you be putting into these problems? Not much at all. Okay? If you try and attempt this problem at the end of the test when your head is buzzing already, what's the odds you're going to enter it into the calculator right? Or even do it in your head correct? Very, very slim to none, which means do not do these calculations in your head. Okay? Everybody laughs at me for writing it out, but guess what? I get it right. Okay? When it comes to me processing these types of problems, my fail rate is our success rate, to be happy. I get them right when I do it in my head roughly 60% of the time. That's not that bad, right? Now translate that to your exam. You get 60% of the questions right. Are you going to be particularly happy when you walk out the door? No. Okay? If your fail rate, or your success rate, sorry, is up at that 99%, but you can do it in your head all you want. I don't care. That sounds fun. Okay? Just telling you, my success rate is really low, and I've been doing it in theory now for 15 years. Okay? It doesn't mean I have the mental capacity to be doing it, but okay, I've been working on it for a while, and I can't do it properly, consistently enough to not skip steps. So please, write out every single conversion that you go through and do. It will help you. Okay? So, next thing I want to do to kind of simplify here, and we'll kind of intro it with this topic right here. This is the same as saying 0.0012 times 10 to the second centimeters. What's the minus sign mean? Okay. Well, we've looked at it before. Skip that. Well, we've looked at it before. We said the minus is bigger or smaller. The minus sign, in my opinion, actually means something else. It's telling you where to run the calculation. Okay? So when we look at these numbers, 10 to the positive 2 and 10 to the negative 2, okay, where are those numbers? In the numerator or the denominator? Wait, where's the numerator and the denominator? Don't you need a fraction to do that? Okay, well, let's make it a fraction. Where are those calculations done? Numerator. Why do we not see the ones drawn on there always? Rhymes with hazy. We're lazy. Okay? There's got to be a better one, right? Okay, so what we're looking at is running those calculations in the numerator. When you have that positive symbol, you don't have to do anything. There's no adjustment. You run the calculation exactly where it shows up. If the calculation is in the numerator, then your answer stays in the numerator. If the calculation is in the denominator, then you run the calculation in the denominator. Okay? What if there's a negative symbol? You change. If your negative symbol, if you have your calculation 10 to the negative 2, that negative 2, or that negative, just means that the calculation of 10 to the power of 2 needs to happen in the opposite location that it's in. Where is that number currently located? In the numerator. So how do we switch it? run the calculation in the denominator. What happens? 10 over, or sorry, that's 1 over 10 to the second. What do you get? 0.01. Right? The negative symbol implies where the calculation should show up. If we go through and propagate this out, simplify one more, 10 to the second is equal to 1 over 100. Okay? This can help simplify your calculations, but it comes up to you with practice on trying to get through it. Okay? So, why bring this up? Well, let's see. Do I have an extra thing I want there? Yeah, we got our numerator, denominator. Nope, I don't want that yet. So let's switch it up now, and instead of doing 10 to the negative 2, I want you to calculate 1 over 10 to the negative 2. 10 to the negative, sorry, that negative is not showing up. Okay. The calculation we want to do is 10 to the second. That's our first calculation to do. Okay. It's currently 10 to the negative second, which means I want to run that calculation in the opposite location of where it is. Where is that 10 to the 2 located right now? Denominator. So run the calculation in the numerator. What's 10 squared? We now have the answer. Okay? That negative is just an implication of doing the opposite of wherever you are. Run the calculation in a different position. If you don't like that, by all means, don't do that. Okay? Your calculator will allow you to solve these when punching it into the calculator. The reason I don't like it, or like the method of punching it into the calculator, is what happens when you make a mistake. There isn't an easy way to follow it. If you set this up and break it down into each of these individual steps, you can see those transitions easier, and it's less likely for me to personally make that mistake. Okay? Takes a little bit of practice getting used to, but it does work out in the long run. There was a hand. It was your hand. You good? Okay, so